In this video, I'm going to talk about normalization and how normalization is preserved for all times. So this video is part of a playlist on quantum mechanics. You can find the link to the playlist in the description below. Now I'm going to show you what I mean by preservation of normalization in a second. But why do we need this property? In the statistical interpretation of quantum mechanics, we need to have a probability density curve whose area is equal to 1. So the area underneath that curve has to equal 1. And it has to stay equal to 1 for all times during the time evolution. Because if it doesn't stay equal to 1, then we're not going to be able to have meaningful probabilities from that probability density function. So I'll show you what I mean. If in the beginning we have a function like this, so let's say we have our probability density function. It starts off at t equals 0. So this is at t equals 0. We're initializing the system, and this is the spatial coordinate x. And let's say we have something like this. There's a bump over here and a bump over here. And as you move away from the origin, as you go towards minus infinity and plus infinity, you're going to end up asymptotically approaching 0. So this is a normalized wave function that we've started off at t equals 0. So at t equals 0, this guy has to have an area equal to 1. So we know that the normalization condition is satisfied. So the integral from minus infinity to plus infinity of the square amplitude is going to be equal to 1. So this is essentially all of this area underneath the curve. So if this is true for t equals 0, I claim that this is going to be true for every single time, for the entire time evolution of the system. Now, let's take another time, a later time t equals t prime. So if we have t equals t prime, and let's draw those axes again. So we've got another set of axes, and we've got the probability density function, but it is at a slightly later point in time. So this is slightly later, after t equals 0. And let's say all of this has shifted over, and now it's over here. So we've got this probability density function. It's clustered around over here. And then as time progresses, it's actually moved over to the right. So this area, all of this area underneath, also has to equal 1. So this normalization condition holds for this guy as well. So this is satisfied. Now, why is this the case? There's actually a video in this playlist where we do a proof of normalization preservation. So we actually prove why this has to hold. But let's think about this from an intuitive perspective. If quantum mechanics describes the universe effectively, and it actually gives us meaningful probabilities, then as the time evolution is going on for this wave function, it has to remain normalized. Otherwise, we wouldn't be able to get those meaningful probabilities out of the wave function. So this is a property that automatically comes from the Schrödinger equation. The Schrödinger equation tells us how the wave function changes over time. So the Schrödinger equation is like the equation of motion for a wave function. And the wave function describes the state of the particle that we're describing. So this property, that the area under the curve is preserved, is essential in the statistical interpretation of quantum mechanics. And in the next video in this playlist, we're actually going to have a look at some of the previous derivations that we've used, and we're going to combine them together and prove that this normalization is preserved for all time t if it is normalized at t equals 0. So if in the beginning it's normalized, it's always going to stay normalized and until the wave function collapses when you measure it. So stay tuned for the next video in this playlist. You can find all the videos in this playlist if you click over here.